which is the RSA paper arises out of the Diffie-Hellman paper in the sense that Ron Rivest read New Directions and he persuaded Adi and Len, who met with the three of them, met weekly to talk about various sorts of mathematics and computing problems. And they managed to solve that problem, Ron in particular, in about 6 weeks, which impressed me very much because I'd come close to finding, I mean, if I were a little less ignorant or had a little better memory, I would have discovered it the previous year. And Marty Hellman and one of his other graduate students, Steve Polig, came closer to discovering it and discovered a system that works similarly. You know, a year and a half or so, 2 years earlier in the UK, a man named Clifford Cox was a brand new employee at GCHQ, and he had a mentor whose name is Nick Patterson. And Nick Patterson had a problem because Clifford Cox didn't have a full clearance yet. So he couldn't talk to Cliff about the things he really wanted to talk to him about. And he remembered a paper that was only secret. He could talk to him about that by James Ellis a few years before. And James Ellis sort of plays the role I play. He wrote a paper outlining the framework of public key cryptography. And one late afternoon, Patterson told Cox about this problem, and Cox solved it before he went to sleep that night. So it took him about 6 hours. And that system, it's called RSA now rather than the GCH cube name for it is C cubed. And it's not quite the same system, but it has the same essential insight, and it's vulnerable to factoring in exactly the same way. And unfortunately, those people, on one hand, more senior people were hesitant to believe in it. And on another, it was computationally very expensive to do it at that time, and they don't seem to have implemented it. I think it could have been implemented for some useful things at that era, but it wasn't. So now what you actually asked me about is Diffie-Hellman. And Diffie-Hellman, it's amazing, interesting, I mean, how simple the mathematics of all of these things is. RSA uses something called Euler's theorem. And you know, when Euler lived more than 300 years ago, and Diffie-Hellman defends on a very simple fact that exponentials commute. If you take, you know, g to the a power and raise it to the b power, you get g to the ab, and do the same thing the other way around, take g to the b power and raise it to the a power, you get g to the ba, but ab equal ba, so everything is fine. And you know, we'd been thinking about this for years, and so one night in late May 1976, Marty saw that you could do that with it, and so we had a solution to half of the public key problem as I had envisioned it. Because I envisioned it in a very, it's fascinating that RSA is basically the solution and the only solution to the problem the way I formulated it. Ralph Merkle, when he saw the paper we wrote about my formulation, contacted us, and he had a different formulation that didn't provide for signatures, but it provided for key negotiation. And he had a solution to it. It's not a strong enough solution, though it's not you can imagine circumstances in which it might work, but what we might be able to get adequate advantage out of it. But Merkel's technique, I think it's just one of the cleverest things ever. Merkel, one party sends, let us say, 1 billion puzzles to the other party. Right? That's feasible today. You can send 1 billion 100-bit, 1,000-bit messages to somebody. And I'm picking that number because you might actually be able to get some amount of security out of that. And so when the person who receives the billion puzzles picks one at random, 674,321. And now these puzzles are hard to solve, but not that hard to solve. So let's say it takes a billion operations to solve the puzzle. You know exactly how to do it. It's not that it takes clever thinking, it just takes computation. So you pick this particular problem and you sit down on it with all your might and you solve it. Okay. And now you have the solution, and the solution is a cryptographic key. So you take that key and you encrypt a 0 with it and send that back to the other person. And the other person now has an encrypted 0, but the other person now knows these billion keys. So the other one runs through the billion keys till you get a P that turns the message back into 0. Okay. And that gives you a cost, loosely speaking, the cost is N for the legitimate communicators and N squared for the opponent. And so those numbers might well allow you, that gives you an extra factor of a billion. And in some circumstances, depending on the speeds of the system and how long the things had to last and so forth, that might actually be made to work. I'm not sure anybody has seriously tried it, but that made us realize that the key negotiation problem could be developed independently of the signature problem. And at GCHQ, one of the problems, they had never seen the signature problem. They didn't, Ellison and Cox and Williamson, none of them saw the signature issue. And so once you have signatures, then you can do much better about key management than to get the authenticity of it as well as the negotiated keys.